I first met him when he was taking Intro to Data Science at Columbia. He's actually written a very popular text analysis package. He really wants you to know that despite writing this great software and being a data scientist at large companies, he has never taken a computer science class. So please welcome to the stage, Adam.
Thank you so much, Jared, for having me. Let me start by, as you can tell, I'm British, so a couple of apologies to start. The first is the majority of the material I'm covering here is not in R. Techniques are available in R, something you could do in R, but most of the code is actually in Python. The second one is that my background game is nowhere near as strong as Rob's. You can see a little slice of downtown Brooklyn out of my window, but Rob's room setting was absolutely top-notch. If you've been following the Room Rater Twitter account, which is looking at people's backgrounds in online interviews, the rooms that their interviews are in, I think Rob is easily at a 9 or a 10. You should really try to get a TV interview in that room if you haven't done so already, because it's great. All right, so I'm here to talk to you about adaptive experimentation, which is three things. It's the name of the team that I'm on at Facebook, which is part of Core Data Science, where I'm a research scientist. It's the name of a family of techniques, and it's also the name of a package called Axe, which is an open source package which my team produces and which is used to apply some of these techniques. So let me go ahead and set up the sorts of problems that we're dealing with here. So we're talking about Bayesian modeling and optimization, and we're talking about Axe, the adaptive experimentation platform. So briefly, the problem setting here is it's an optimization problem where we're trying to optimize a function. And there are a couple of important characteristics about this function. The first one is that the form of the function is not known. Right? It's a black box function. It's not a function where we can compute gradients. It's not a function where we know anything about the relationship between the inputs to that function and the output. And the other thing about this function is that it's computationally expensive to evaluate, which is to say, you could imagine this being the case in two of the canonical applications of these techniques, which are hyperparameter optimization for machine learning applications, where retraining the whole model is expensive with a different set of hyperparameters. Or you could think of an experimentation context where the model is a relationship between some continuous or discrete treatment variables and some outcomes, where in order to measure the outcomes, you have to run an experiment and see something happen in the world. And so in both of those cases, you want to minimize the number of times you do this evaluation. You want to sample as few points as possible in order to optimize this, again, unknown function. So the applications here, as I said, hyperparameter optimization for machine learning problems, experimentation in particular, where we have multiple continuous treatments. So you can think of this as, continuous variables which determine something about the treatment which the experiment is putting in place. Another case, like kind of cute application of this is you can think of this being used for physical experiments as well, right? Not just abstract online computer science type things, but in manufacturing. So there's a nice report about this from Google about using these kind of techniques to manufacture cookies to figure out the optimal cookie recipe. And the idea there is that a cookie recipe is just an experiment with a bunch of continuous parameters, right? The amount of butter, the amount of flour, the amount of chocolate chips, and the time that you bake the thing for, all continuous parameters. And for some combination of values of these things, you're going to have the optimal cookie. All right. So the solution to this category of problems that you come across in Bayesian optimization is in order to optimize this unknown function, we're actually going to optimize a different function. So the function we're trying to optimize is the target function. But because we can't compute gradients on that or speculate about the values of that function for unknown inputs, what we're going to do is fit a surrogate model. This is a function which aims to approximate that target function. And so you can think that we've evaluated the target function for some observed points, right? We've baked some cookies and seen how good the cookie is. And so we fit a model to those points we've already observed, but this model allows us to extrapolate to other points which we haven't observed. And importantly, because this is a Bayesian approach, this function also allows us to quantify uncertainty. So you can imagine this surrogate model is going to try to pass through the points we've already observed, and it's going to have low uncertainty there because we have actually observed those points. But for other points, it's going to extrapolate, it's going to make a prediction, and it's also going to tell us, if this point is very far away from the points we've already observed, then it's probably highly uncertain. We make a point prediction, but there's a range that prediction can fall in. And then we use this surrogate model to select new points to evaluate based on the acquisition function. And the acquisition function is just based on all of the predictions we can make from the surrogate model, which is the most useful next point. And the difference between acquisition functions is how you parameterize most useful, right? You could think that the naive thing to do is we just select the point which our model predicts would be the maximum, but then what do you do next, right? And then we iterate. And I'll get into a little bit more detail of like real world acquisition functions in a bit. And then we iterate this process. So we observe some more evaluations of the target function, we fit the surrogate model, and we keep going until we get to some optimal point. Okay, so just to describe the setup graphically, what you can see here is a representation of a very simple Bayesian optimization problem where we have one continuous parameter that we're trying to set, which is on the x-axis and ranges between 0 and 12. And we have the output, the value which we're trying to optimize on the y-axis. So we've observed, in this case, 5 points. We have the x's for the evaluation, the point estimates. We have some sort of confidence interval that we've observed that depends on the noisiness of the process. We have in gray the unobserved true function, which we're trying to optimize. And then the blue is this Gaussian process, the surrogate model, which we fitted. And as I said, it passes through the 5 points, but it also gives us this band around it, which quantifies the uncertainty. And you can see that in the regions where we haven't observed any points, the uncertainty is high. Okay, so what's next? Next, we calculate the acquisition function. And in this case, it's something like expected improvement. And the idea behind expected improvement is that we're going to try to find the point where, based on the current maximum that we've observed for the function, and our expectation that if we sample this next point, the optimal value of the true function is going to be the highest. And you can see that here that the expected improvement is actually pretty high in this uncertain region, right? And in fact, the optimal value marked by the purple line, the expected improvement is higher in this uncertain region because even though we haven't observed it, our Gaussian process says there could be some pretty high values here, but we don't know what they are. Okay. So as we go through this iterative process, you'll see that we observe an additional point here based on expected improvement that redefines our acquisition function. Then we observe another point, and all throughout this, we're reducing the uncertainty across the board. And then we get to the point where we think it's more or less optimal, and we can stop. The same thing also applies in, I should say, two-dimensional cases, obviously, and in fact, relatively high-dimensional problems can be solved in this context. Another thing that's worth noting is that the selection of the initial points is kind of an interesting problem too. You could imagine doing it with a grid search, like trying to cover the space of parameters, but also you could imagine doing it with some sort of thrifty initial design. And the idea here is that instead of doing a grid, we want to choose some sort of space filling function. So again, remember, trying to minimize the number of points that we have to actually evaluate, a space filling function to try to cover all of the space and give us some idea of what's going on without having quite so many points as a grid. Okay, so now let me talk about ACS. The way this works is that ACS sits between either people trying to manually optimize these processes, or it can be integrated into a larger system, and it goes through this experimentation loop where it can control experimentation in outside systems. This could be A/B tests, it could be a machine learning system, it could be benchmarking, it could be an ML system. It also supports human-in-the-loop optimization, where you have to go in and intervene in order to evaluate the function. And it'll give you all sorts of nice features, including the Bayesian modeling, and also some visualizations of real data, which allow you to figure out trade-offs between multiple objectives, if that's your sort of problem, and also look at these surrogate models to see what your space, the space of your function looks like. All right, so now let me switch to the demo. Okay, that seems to be working. All right, so the idea here, this is based on an example for tuning a convolutional neural net, which is available on the ax.dev website as a tutorial if you want to work on that as well. So the first couple of cells here are just doing some setup. We're going to be training this on MNIST. We're choosing a small percentage of the actual data so that this demo can run in real time while I'm talking. So we do some setup to load the right libraries. We have these train, validation, and test loader sets. I should say that underlying this, Axe is doing the hyperparameter tuning part. The actual CNN is implemented in PyTorch. Okay, so what's the first thing we need to do in order to be able to optimize this function? And this function, again, is going to be the function from the hyperparameters of a convolutional neural network to the accuracy of that CNN on this set of MNIST. So the first thing we need to do is define the function we're going to evaluate. So let's do that. So we're going to call it train evaluate, because it both trains a model and evaluates the model. And this is going to take in a parameterization. And the idea here is this is a dictionary which specifies the values of the parameters that go into this function. And within this function, we'll create a CNN. We will then train that CNN. And some of this is using helper functions, which are defined for this tutorial, but you can do the same thing using raw PyTorch. So we'll train this CNN. We'll train it on the training data. And we'll specify parameters. Okay. And a couple of counting things we have to do. Okay. So this will result in a neural network trained on the training set. And then we need to return the output value for this function, right? So what we're going to do is we're going to use this evaluate function, which will give us the accuracy for the network on the validation set. Valid loader. Type again, dtype, and device equals device. Okay, so we've defined this function. So let's just evaluate it once to see what it does. So we'll set a manual seed for PyTorch for reproducibility, and we'll call train evaluate. And here we're going to use the default values that PyTorch would use for these two hyperparameters for training the CNN. So we're going to use a learning rate of 0.001, and we're going to set momentum to 0. Okay, so I have to actually. Did I type it? There you go. Okay. So this takes a little minute to run. You can see that we're achieving 10% accuracy on a validation set. It's not particularly great. Okay, so now let's go through the actual optimization part of this. So we're going to set the seed again, and now we're going to use the actual ax function. So this is a function which will return a few different things. I'll define those in a moment, but let's just call optimize. So we're going to optimize, and we have to specify what parameters we're trying to optimize. And here, again, this is just going to be the learning rate and the momentum. We have to give Axe a little bit of information about this. So the first one is a learning rate. It's called LR. The type, it's going to be a range parameter. That is to say, it's a continuous variable which can go between two bounds. And we have to specify those bounds as well. So this is part of the search space, right? The area within which it's going to search. And that's a reasonable range. And we're also going to specify this as a log scale parameter so that we're sampling from a log scale rather than treating it as a linear one. Okay, so that's the learning rate parameter. We're also going to specify the momentum. And this is also a range parameter. It's not log scale. And by construction, this one ranges between 0 and 1. Okay, so that's the parameters. We also have to specify the actual function. Evaluation function is train evaluate. And a name for the objective, just so we keep track of that. Not that it's the label. Okay, so this optimized function returns a few different things. It returns the best parameters. It returns the values. It returns experiment and the actual model itself, in case we want to look at that later. All right, so I've set this running, and just in it'll take a couple of minutes to run. Let me just describe this output here. So what this is telling us is that we're using Bayesian optimization, yes. We're using a particular generation strategy, which is a combination of generating those initial points that we're going to look at, and we're using a Sobel function for this, which is one of these random space-filling functions. And then we're using GPEI, which is, as I said, Gaussian process with expected improvement as the acquisition function for the subsequent trials. And by default, we're running 20 trials. On the actual full MNIST data set, this takes, on my machine, maybe 5 minutes to run. I cut this down for the purposes of the presentation so that I have time, which I'm getting perilously close to. And that should be complete. OK, so let's see what parameters we came up with. So we ended up with a learning rate that was smaller than the initial one and a momentum that's somewhere around 0.4. And we can also look at the values that are returned by this. So here, the values are the values of the function we tried to optimize, and we've achieved an accuracy of 0.7. And this is telling us the variance of that measure. And that can be useful if we have multiple outcomes. All right, so let me wrap up. So hopefully that's giving you a bit of an idea of the sorts of problems you can use Bayesian optimization to try to solve. And if you want to learn more about Axe, contact me through Hopin, come to axe.dev, have a look at the tutorials, and figure out whether there is an application which you think might be useful for any of the problems that you're facing.
Thank you very much, Adam. Live coding a neural network at a conference is brave. That was pretty awesome. Thank you very much for doing that.